Today is December 1, so we have a class today, clearly. And our last class will be December 8. What do you have in middle? December 6. Yeah, and your exam is December 15, right? So December 14th, I don't think I should be having a class.
Okay, our last day class today.
Yeah.
Our exam is
December 15th. Or whatever it's written on the website, you can go and see. What's written on the website?
14th.
Okay, then it's 14. Yeah, these days I even have to set up a Google Calendar with my dog. Go for a walk. All right. It's become terrible. Yeah, it's December 14. Yeah.
If we don't get the last homework, is it considered as a drop?
Of course. I won't. It's up to you, but it's terrible. I will be judging you for the rest of your life. I promise I will be judging you. No way. I mean, you come to me and I will be like, why won't you do it? It's so much fun. Of course, I will honor the drop comment. There is no question. If you're so overwhelmed that you really don't want to do it, that's fine. I have done similar things in grad school, I confess. But my professor judges me to this day. So it depends on what you want, Do you want my appreciation for the rest of your life? It's bigger than great, right? But think about it that way. It's a fun problem. It's a fun paper to read. And I thought it should be exciting, but up to you. Okay. Today's class will be short. So December 6th today and December 6th's class will be short. I don't want to cover that much material. We'll do what we do today. December 6th, I will talk a little bit about chemical equilibrium and the concept of activity. So these two will be relatively short classes, and December 8, I will do a recap of the full semester. Okay, the key concepts are here. I mean, it's going to be hard to recap every single thing, but we will see what we can do. And then December 14 is the exam, which will be here in this room. So be here on time. And again, Alex has already asked, you cannot bring a bed sheet for your cheat sheet. Something of this size is fine, If it's a bit bigger, I won't go around cutting its edges. So let's talk about lever rule. So what is lever rule? It tells us if we are looking in a phase diagram, and it applies to temperature composition phase diagram. So this is temperature, this is composition, which is going from 0 to 1. This is short classes. So today we will finish a bit early. December 6th, I'll probably start a little bit later. And the idea is if you have a two-phase region, so yesterday, the other time we talked about a two-phase region, which looks something like this. A lever rule applies to any two-phase region, okay? In the homework problem, when you see lever rule application, I'm not showing you where the ends are of the boundary, right? It's some two-phase region, it doesn't matter. It won't help you with a three-phase region. You could write down a similar lever rule, but I don't know what it will look like. So it applies to two-phase regions. And the idea is here that if you have a point O, at this point O, the system, and let's say this is vapor, this is liquid. At this point O, the system will exist as a combination of a vapor phase and a liquid phase. The vapor phase will have concentration of B equal to X1, right? You get it by, yeah, go ahead.
Does the way that the lens points matters?
No, just nothing matters. I could just remove all of it. I could make the lens whatever it is. Really, no difference. Some boundary. And even the lens is because we are doing a simple phase diagram, but it could apply to, for example, complicated phase diagrams, which look something like this, and you could be doing lever rule in this part of the phase diagram. As long as you have a two-phase region, look at the two boundaries. That's the idea here. Okay. So I'll point it applies here too. It applies anywhere. So at point O, due to the common tangent construction, it will exist as a mixture of vapor and liquid. The amazing thing is that it doesn't matter whether the point O is in the middle or to the right or to the left. The concentration of the vapor that forms will always be X1. Okay, and this I cannot drive home more importantly. It's super important and it's fundamental. It's from chemical equilibrium, right? It's because chemical potential has to be equal. That's what it follows from something known as the common tangent construction. It's not kind of trivial why it should be like that. And over here, you will have liquid, which is formed with the concentration X2. But clearly, if your point O was over here, it would be all vapor, right? With my black line. And if your point O was here on the right side, it would be all liquid, right? So the question is, for some arbitrary point, what is the concentrate? What is the amount of liquid? What is the amount of vapor? So Lever rule allows us to calculate it. The way it does it is by calculating this length of O from the nearest phase on the left side. In this case, it's vapor, so LV, and calculating the length to the phase on the other side, which is small l subscript capital L, okay? Because that's the distance from the liquid. And then Lever rule says that the number of moles of liquid multiplied by number of mole by the length LL should be equal to number of moles of vapor multiplied by LV. And we saw last time how this rule makes sense at the boundaries. If you are right above X1, then LV is equal to 0. The length from the vapor line is 0, which means NL is 0. The number of liquid moles is 0. So the question is, how do we prove this in general? Some of you tried, right? You probably even succeeded in proving it, but let's see how to do it. It's simple if you understand the fact about the common tangent construction. That if you understand that the concentration of the liquid will always be X2 and the concentration of the vapor will always be X1, then it is easy to prove. So in order to prove this, we are going to look at point O. We are going to calculate the number of B molecules at point O in two different ways and equate it, okay? The number of B molecules at point O, Jared, your homework is in midterm is here. The number of B molecules at point O is some number, and we are going to calculate it using two different techniques and say that it should not depend on the technique we use. So at point O, we calculate B in two different ways. What would be these two different ways? Any ideas? What should be the first way or the second way? How do we calculate it? If the number of liquid moles is NL and the number of vapor moles is NV, then if we add up NL plus NV, that is the total number of moles, right? What should we multiply it by in order to get the number of moles of B? XB. That's one way of doing it. Right? Everyone agrees this is the number of moles of B at point O, because point O, the mole fraction is XB. Okay. Is that the only way? Or could we do it in some other way? That is the tricky part. And I want us to think. Is this the only way? Aurelia, what do you think? Where is B coming from? Yes, but it's got to be either vapor or it's got to be either liquid, right? So I could go separately and count how much B do I have in vapor and how much B do I have in liquid. That would give me the number of B molecules, right? Do I have any idea how much B I must have in the vapor phase? The concentration of the vapor phase is X1, right? So the moles, what is this? This is like a percentage, right? This is a fraction. So the fraction of B in the vapor phase is always X1. On top of that, I know that the amount of vapor phase is NV, right? So the number of B molecules, sorry, coming from vapor phase is going to be NV multiplied by X1. And this happens only because of the common tangent rule, because we know the vapor is always of concentration X1. Otherwise, this would not have happened. And then it will also come from NL, right? What's your name? I forgot. Yeah, Abhin Dev. You have never spoken. You tell me. Don't judge me. I literally woke up at 4 a.m. last night. I thought, Abhin Dev has never spoken in class. I'm going to ask him a question. I'm not kidding. So tell me now. So I calculated the number of moles of B in the vapor phase. Now B can also come from the liquid phase. How much would that be? X2 multiplied by? Perfect. Thank you. My dream has come true. Good. So let's see if we can proceed from here. I mean, this is all we need really. Why? Because now if we multiply it out, we get NL multiplied by XB plus NV multiplied by XB is equal to NV multiplied by X1 plus NL multiplied by X2. So let's bring NV to the right side and NL to the left side. So what do we get? No, sorry, the other way around. You'll have a minus sign. So you see my point. Sorry. This way. So let's bring NV to the left side. So what do we get? We get NV multiplied by XB minus X1 is equal to NL multiplied by X2 minus XB. What is the connection between XB minus X1 and LV? It's the same thing. I mean, apart from a fraction, right? But it's the same idea if you multiply by total length. This means that NV multiplied by LV is equal to NL multiplied by LL, and we have just proven it. So the proof is really simple. The subtle thing is this part that Abhin Dev helped us with, and Aurelia also helped us with. Why should we write this concentration? And this is a consequence of the common tangent construction, or it would not have. Okay, so this is Lever rule. In the homework problem, there is one problem where you can use it and just get to terms. It should be easy. I mean, this homework is very easy. Even though Keith says he's not going to do it. I mean, I'm so sad. It's so easy. Why don't you want to do it? Huh? What? You are also not going to do it? You will also not do it?
I want to do it.
You want to see? There you go. I thought there is like a resistance or a revolution. Omar's already checked out. He did not do the last homework. I'm like, yeah, I'm done. Does anyone know he's alive? Vanessa, huh? He's alive. I should give a pop quiz today. And then you can all thank Omar. So this is
No
Lever
problem.
rule. Oh, he's on Zoom. You are the one coughing. You are alive. Okay, clearly you're alive. Or you have a very good AI.
Oh yeah.
Good. So this is lever rule. It's simple, it's very useful, and you can see why it's called as a lever, right? You're measuring the distance and just that. It's once you go to a very, very complicated phase diagram, it still applies, and that's where it starts to be powerful. So with common tangent construction and with lever rule, you can look at a phase diagram and say which phase is going to form, what is going to be the concentration in that phase, and how much of that phase is going to form, right? So you're ready to read very complicated phase diagrams. It applies to even, we did not talk about, I want to talk just a little bit about ternary phase diagrams, how to read them. I won't go into their construction. So this is when you have a two-component system, right? And we could just draw an x-axis and talk about two components, the mole fraction of one. How about if you have a three-component system and you want to write down a temperature composition phase diagram? How would you do it? Nick, what do you think? And I don't want you to make a 3D picture. I mean, that would be one way, right? To have a box where one coordinate is x1. So let's say I have three components, Nick, A, B, and C. Earlier, I had only A and B, right? So I could get away with just drawing XB because XA plus XB is equal to 1. In a three-component system, apart from temperature, how many mole fractions will I need? 2, right? Because we always know XA plus XB plus XC is equal to 1. So we need to draw two things. So one way could be to draw something where XA goes like this, XB goes like this, and we do temperature on some axis coming out of the paper. that's kind of clumsy, right? And we will all have to work with like big boxes of phase diagrams. That's not practical. The way people, some of you maybe know it, how it is done. If you do that, then don't answer. But if you don't know, can you think of a way, how should we plot this in a smart way?
Two phase diagrams.
Yes, that's one way. Yeah. I will, instead of carrying a box, I will carry a stack of papers, right? that's one way. But in general, when you want to, yeah, go ahead.
Triangle.
Yeah.
Triangle and contour plots, right? In general, when we have to show high dimensional data in 2D, we use contour plots, right? So that's the whole idea. So what we will do here is to draw a triangle, and it's known as Gibbs triangle. And this, I want to show you so, because if you see a ternary phase diagram, you know how to read it, okay? And we won't do much about it. Here, every corner represents pure component. So one corner is pure A, the other corner is pure B, other corner is pure C, okay? And just focus on A. So now we will draw a line. So this is going to be, first of all, an equilateral triangle, okay? And when we draw a line, this line is going to correspond to constant compositions of A, okay? Lines that are parallel to the other side. Lines that are parallel to the edge facing A will be lines of constant composition of A. So we can draw lines like this. These are constant composition lines for A. So for example, this one will be XA is equal to 0.9, and this one will be XA is equal to 0.1, right? And this edge itself is XA is equal to 0. You don't have any A, right? Now we will draw another set of lines corresponding to B. Where this one corresponds to XB is equal to 0.9, and this one corresponds to XB is equal to 0.1. And we will draw a third set of lines corresponding to C that runs parallel to the other edge. And this one is XC is equal to 0.9. This one is equal to XC is equal to 0.2, and you get the idea, right? And that's it. Now you can map things here. In any given region, you know this is probably going to be equal concentration of ABC, right? And you can go and mark your phase. So then it will look just like your normal phase diagram. You will have regions with different phases marked. So this is known as a Gibbs triangle. If you have 4-component system, this is not going to work. I don't know how to draw those. There, of course, nature has many systems with more than 3 components, but this is how we can draw three diagrams, okay? So we are not going to talk about this in the class, but this is something you might come across in your research, so you won't be like completely like, whoa, what? Yeah, but you know, you can think. Okay, so let's go further. That's liver rule. What I want to talk about next, which is really the last topic in phase diagrams, is the concept of phase separation. So last class we saw that fully mixable liquids A and B, or fully mixable chemicals A and B. What do I mean by fully mixable? What fully mixable, I mean that their free energy of mixing, delta G mixing versus composition XB was always negative, right? That's it. That was fully mixable. Anytime you add, they keep mixing. It's like, oh yeah, mix more. And it keeps mixing more and more. It just keeps getting negative. We still got phase separation, right? In a sense, we still got different phases existing. Why did we have different phases existing? Because, well, there were 2 phases, right? And it happened due to the composition, due to the competition between liquid phase and vapor phase, right? So at very high temperature, for example, we had, this was G liquid and this was G vapor at very high T. As we decrease, as T went down, we had a temperature at which the liquid, all the curves, as temperature decreases, free energy curves go up, right? Swerman proved this for us, right? Swerman, dG is equal to V dt minus SdP. And partial G by partial T at constant P is equal to minus S, right? And S is always positive. So as temperature goes down, free energy curves go up. This is true for like everything in the world. There is no violation because there is no ideal gas assumed or anything, right? The violation means you're not in equilibrium. That's what's going on. Or your system is too small. You have finite size effects. So at some temperature, we get a crossover between the two phases. And then we start to get phase separation through this common tangent rule. So we saw two phases existing separately if we had, even in a purely mixable system, if we had two phases that compete with each other. Today, we are going to talk about how this can happen, even for just one phase, how we can get phase separation, okay? And this will happen when the liquids are not fully mixable, they are partially mixable. We already saw an example of this in the regular solution system, and we are going to revisit that and look at it carefully. So today, we are going to talk about partially mixable liquids. Who here loved organic chemistry? I still love it. Oh, look at them. Cool. Can you tell me of two partially mixable liquids from your organic chemistry lab? Water and
Partially ethanol.
diethyl ether. That's what I have written. There must be so many else. So there are examples of two liquids that do not mix. I mean, and even water and milk are not really fully mixable, right? And yeah. So we have, I mean, water and most oils do not fully mix. It's as simple as that, right? Water and oil, you get a layer, something that comes up to top. And it's not that it's pure water and pure oil. The layer that comes on top is probably oil with some water, and on the bottom you have water with some oil, right? But you get phase separation. So we are going to try to understand this. For this, the phase diagram, and this is what you see in the homework set in one of the problems, not a parabola. The phase diagram for this will look something like, so you have again XP, we have a two component system where XP goes from 0 to 1. And this phase diagram, even in a single phase region, tends to show a dome. We are going to understand what is the origin of this dome. Where does it come from? So all of this is single phase region. Okay. This is all single phase. This could, for example, be liquid. And in the middle, so this is P is equal to 1. We have single phase region, you have single phase region, and in the middle, you have a double phase region, P is equal to 2. This curve that you will see in phase diagrams, it has a name. It is known as the mixability gap. Okay, and you will understand where it comes from. Sometimes inside this dome, and this is the critical temperature, this temperature at which the dome peaks up. Inside this dome, there is another smaller dome that is not really an equilibrium phenomenon, but due to kinetic effects, it almost looks like one. It's sometimes not marked, and we will understand where that one comes from. This inner dome is known as the spinodal gap. And we understand what both of these are. And if truly in equilibrium, it won't matter whether you are in spinodal gap or outside it, you will get the same structure. But the mechanism through which this second phase grows out of the first phase is very different, depending on whether you are inside the spinodal gap or whether you are in this region, the red one, or whether you are in the blue region. The mechanism of growth is completely different, and we will understand what it looks like. So let's try to understand what this mixability gap and spinodal gap is. In order to do this, let me remind you of the free energy of mixing. Delta mixing G, we derived, and we are using a regular solution model to motivate this, but it is much more general. So regular solution model, recap, our mixing free energy was omega XA XB plus RT XA ln XA plus XB ln XB. And the second term was always negative. Remember, because XA is between 0 and 1. So it's positive, but log of something smaller than 1 is always going to be negative, right? So that's always negative. So it's all about the sign of omega. If omega is also negative, then it's boring. It's basically a fully mixable system, right? There is nothing to talk about. So let's think when omega is positive. In this, remember we had two cases, low temperature and high temperature. At high temperature, the system behaves again as a purely mixable system. Why? Because the entropy term dominates, right? The second term starts to dominate. At high temperature, this term over here is what dominates. And it doesn't matter that omega is positive. You get nice behavior. We got interesting behavior at low temperature when there was competition between energy and entropy. So let me remind you what it looked like. So we drew the curves, and I will draw two sets of curves. We are talking only about omega positive. Okay, for omega positive, we will draw something for high T and low T. And we have the line, and so we are plotting various quantities. This is the line corresponding to 0. The minus T delta mixing of S is always negative, right? It goes down. At high temperature, it is more negative. At low temperature, it is relatively less negative. I think you should do the homework. Yeah, it's so sad. If you don't read the paper, if you're so confident about it, at least do the first two problems. The first problem especially will force you to think about phase diagrams, where the free miracles come from. Okay, and please do it. I'm very sad, man. Yeah, go ahead, Gavin.
This is for make it greater than 0?
Yeah. I haven't talked anything about the first term. Go ahead.
Just a question about the picture. So is there overlap between these gaps, or are they completely separate? So like
Which the first picture?
Yeah, like the miscibility gap and the.
They intersect only at the critical temperature.
Okay, so that's the only point in
Yeah,
this graph
yeah,
where you
yeah,
can be in both.
yeah.
Okay.
So now the question is, what happens to omega XAXB? So omega XAXB does not depend on temperature, right? It's temperature independent. And that's going to look like a parabola. And that's going to behave like this. And in this one, it's going to behave like this. It's the same curve. The first one, when you sum the red and black, you get something which is always negative, right? Because the black dominates. So in the first one, the delta G mixing looks something like this. In the second one, if the temperature is low enough, you can start to get complicated behavior. At the either end, the black will always dominate. Do people remember why, or have they forgotten already? Huh? It's the slope. It's L'Hospital's rule, right? It's this minus the entropy x ln x drops down with a slope of minus infinity. So at the end, it's always going to be negative. But in the middle, it might start to dominate and then again goes back to this as the end. So we can get this behavior at low temperature. And this is what I'm going to focus on the blue curve. Okay, so let's forget about the red one. Let's forget about the black one. Let's go to the next page and draw a new figure only with the blue one. And let's try to understand what's going on. So going back to this phase diagram that I drew on top, if the temperature is high enough somewhere over here, you are going to get only one phase, right? It's pure mixing. If the temperature is low, it's corresponding to something like the green line, then you might start to get this behavior. And let's try to see why two phases are coming from this and what is this miscibility gap and what is this final decomposition. Okay, let's try to understand it. So next page, I'm just going to draw this blue curve in the right figure, in the bottom right figure. And I'm going to draw it in a big box because we're going to spend some time understanding it. So I'm just drawing delta mixing G. Versus XB 0 to 1. And we have a curve that drops down with a slope of minus infinity. Then it goes up. Actually, I want to do one thing. It drops down. Then it goes up. and then it again drops down, and then it comes something like this. It could be symmetric, it could be asymmetric, I don't care about it, okay? So this is omega positive, low enough temperature. So let's mark a few things over here. First of all, one thing we should do is to find our common tangent in this system, right? So how do we find a common tangent? Remember last time when we did a common tangent, we had two curves, right? Two different curves, and we found a common tangent. Here we have only one curve, but we can still think of a common tangent construction. There is only one line which is a tangent to this curve at two different points. So last time we said there is only one line which is a tangent to curve 1 and a tangent to curve 2. Sorry, Omar, I'm not sorry. I don't know why it's in Zoom. I'll draw it here. Last time we drew some and then I will erase it. Last time we had a curve like this and we had a curve like this. And we said there is only one line which is tangent to both of them, right? That was the idea. Here, we don't have two curves. We have only one curve. But if you think about it, if I was to kind of mask out this part, it kind of looks the same, right? That's the idea. So there is only one line which is tangent to both of them, and you can draw it. It's going to look maybe something like this. So this is my common tangent. From this figure, it looks like the common tangent crosses the minimum of both little dips that you see, like over here it is at the minimum, over here it is minimum. That is just because I drew it this way, right? The common tangent could be wherever it wants to be, but you can construct the common tangent. Let's find the concentrations. Let's mark them and we will give them a name. Let's call this X alpha. Let's call this X beta. Now, if we are at this particular point 1, we have a certain free energy G1, right? But last time we saw that instead of this, if we drop down to something over here, and instead of existing as a single phase, if we go into a combination of the red point marked over here and the green point marked over here, we can have lower free energy, right? The free energy drop down. The free energy of this point is going to be, let's call this as G alpha. Let's call this as G beta. So the free energy of this point is going to be some concentration G1 multiplied by G alpha plus some concentration C2 multiplied by G beta. And it's always going to be under the curve. This actually goes back to something wonderful we studied about entropy. This is a concave function, right, in the middle. So anytime you draw, and this is actually the definition of a concave function. If you go to Wikipedia and you look up what is a concave function, you will find the definition of a concave function is that if you draw a line connecting 2 points on the function, it will always be lower than the point in the middle, okay? Imagine if the free energy curve looked something like this, but we are actually going to talk about it in just a moment. So this is going to be always lower, right? So it's going to change into two phases, a mixture of a phase alpha, where the mole fraction of B is X alpha, and phase beta, where the mole fraction of B is X beta. And it doesn't matter whether you are at point 1, whether you are at point 2, whether you are at point 3, you will always change into the same two phases. What will change is the ratio of these two phases. Do we know how to calculate these ratios? Lever rule, right? If we have a phase, we don't have a phase diagram quite here, right? But if you could draw the free energy at different temperatures, we could draw a phase diagram and get it from lever rule. Actually, do we need lever rule or could we just calculate it from this picture? Do we have the lengths already over here? I think this is the length, right? This is the length that we had in the phase diagram. That information is already here. You can calculate what that quantity is going to be. So that's good. But now I want you to think about, and I will remove this 1 and 2 and 3 because I have to draw a little bit more over here. Now I want you to think about another point, which is also in between this alpha and beta, but it lies up here, okay? Let's call this one as point number 2. Same common tangent construction applies over here also, right? From this point 2, you could drop down and change into this concentration and exist as a combination of alpha and beta. But something very peculiar can also happen at point 2. What is that? At point 2, you could drop down as a combination of this one and this one. They won't exist in equilibrium, okay? So I'm not talking about two phases existing in equilibrium. Alex, pay attention. Do you know spinality composition?
It's obvious.
Huh?
It's obvious.
Tell me what's going to happen next. What's special about point 2?
You will become positive alpha and at point X alpha and
Well, that's why I'm saying pay attention. No, something mysterious happens. Okay? So pay attention, stay with me. You're going to be rid of me in a couple of weeks until the end of January. I talked about alpha and beta, but here I drew 2 other points, arbitrary points, okay? Or something else, another line which looks like this. Each of these points, let's draw it a bit more clearly. So the point I'm trying to make here is this point 2 could change into a combination of these 2 points, or a combination of these 2 points, or a combination of these 2 points, and their free energy will be lower than the free energy that you had earlier, right? At the top of the point 2. They're not going to be in equilibrium. But something interesting has happened. Tiniest fluctuation in the system, tiniest fluctuation of concentration will lead to a lower free energy. This was not true over here. If I go back here and try to do the same test, at this point, if I drew a tiny fluctuation, the free energy would actually go up. Do you see that? That's why I said, it's fine. I find this very, very interesting that if you're over here and you did a tiny fluctuation, your free energy is not going to go down, it's going to go up. But up here, a tiny fluctuation will lead to 2 phases forming, which are not in equilibrium, but their free energy is lower than what you had earlier. And it will keep growing and growing and growing. What is the difference between point 1 and point 2? What distinguishes point 1 and point 2? Second derivative. There is a certain inflection point. These 2 are the inflection points at which partial square g by partial xb square becomes 0. So it's inside the inflection point that you get this very peculiar behavior. So if you had a system at a composition, and this can be seen in a microscope, and it really can be seen all the time in a microscope. So if you have a system at point 1 versus point 2, at point 1, the system can exist, can lower its energy only if it has this big fluctuation, okay? Where you form one phase which is much lower in B and one phase which is much higher in B. So at point 1, the growth mechanism, the mechanism through which the new phase form is known as the nucleation and growth mechanism. In life, this is known as the rich getting richer and poor getting poorer mechanism, okay? So if you have some money, it does not mean you will keep getting richer. But if you have a lot of money, it's very easy to keep getting richer and richer, right? It happens all the time. It's also known as Ostwald ripening. Go ahead, Jared, you have a question? Okay, so nucleation and growth means that if you had a tiny fluctuation, it's not going to survive. But by sheer chance, if you had a fluctuation in composition where you form something which is very low in A, then it will survive, or very low in B, it will survive, okay? So why do fluctuations happen in system? That's just thermally driven, right? Things are moving all the time. And next semester is all about fluctuations. Statistical mechanics is really all about the study of fluctuations. So even an equilibrium system is always fluctuating. In fact, I have a heart rate monitor here, and if my heart rate was constant 40, that would mean I'm probably dead, right? It should have fluctuations. So point 2 is very different. Point two, even the tiniest amount of fluctuation is great because you just drop down in free energy. Point two is what is known as spinodal or barrier-less growth. And all length scales, and it's really, really bizarre because I drew all these lines, right? Any of these lines is okay. You can fluctuate by a small amount, you can fluctuate by a large amount. If you fluctuate by this mega amount, then of course you will reach equilibrium. But it is a phenomenon that is going to happen at all length scales. If a phenomenon happens at all length scales, in physics we have a name for it. Anyone remember what it is? Starts with an F, ends with an L. Next letter C, R, fractal. It's a fractal-like mechanism. You know, you must have read some point about Mandelbrot set and things like that, or the coastline of an ocean, right? It looks kind of similar from the airplane. If you go down, it still looks similar, or a snowflake, right? You can keep zooming in, it looks the same. So if I was to draw a picture that was taken from the microscope, in both cases, so when I was undergrad, I would do these things and understand the theory very well, and go to the lab and try to take a picture. And I never got the right picture because in microscopy, the biggest challenge is sample preparation, right? And the more I would prepare my sample, the uglier it would get. Which is kind of terrible. But I can do it in computer simulations. So in nucleation and growth, you will find big enough nuclei that exist. Okay, so this will be something like phase alpha, this will be something like phase beta, maybe in the middle, you have some other blobs of phase beta, and you're surrounded by phase beta over here. You know, if you have big blobs of alpha and beta that exist. In spinodal, it's kind of hard to draw, but it's going to look like at any resolution, you will find alpha and beta coexisting. You zoom down inside it, and you will again see alpha and beta coexisting because it's just so funky. Okay, and if you remind me on Slack, I can show you some movies, or if you just go and look up on Wikipedia. So oftentimes it also looks like, yeah, the more I dry, the more confused you will get. But hopefully the physics is clear that any tiny fluctuation is like, aha, energy lower. It's not in equilibrium, and it won't reach equilibrium until you reach those two concentrations, right? But it might look like it is in equilibrium because it is kinetically trapped, right? It has to surmount a big barrier to get there. So now if we go back to our phase diagram, the miscibility gap comes from the common tangent construction, right? We draw a tangent and we see where is the point where it meets both curves. Where does the spinodal come from? That comes from the inflection points, okay? So what do I mean by this? I could draw this free energy curve at different temperatures and see where my inflection points are. And this is why I keep insisting to Kiet, even though he says he wouldn't do it, to do the last homework. Now I think he will do it. I've bothered him so much. Because for the first problem, this is exactly what you will do. Okay, you will draw these curves at different temperatures that will help you understand this material. Okay. Any questions about this? So people use these things to model a lot of things in life, not just biology and chemistry, but also society. I visited my friend who works at Facebook Research in New York, and he was using spinodal decomposition to model how people talk to each other on Facebook, right? Sometimes there is an opinion which spreads like boom, 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 right? You tell it to one person, and immediately it goes everywhere, right? And certain opinions, you really 50 people or 100 people need to be convinced of that opinion, otherwise it does not grow. You see what I mean? And you can see why certain opinions might belong to first class, the other opinion might belong to the second, right? And next semester we will talk about Ising model, which also gives us an indication into how these things arise. And so this is it for phase diagrams. I'm not going to talk any more about phase diagram. As I said, today's class is short. Tuesday's class, I will start a bit late. I will confirm on Slack when to start it. Okay, so it will be shorter class, but instead of finishing early, we will start a bit later. We'll most likely start 11:20, but give me some time. I want to see how much I have to cover. And not earlier than 11:15 for sure. But I will confirm through email and on Slack. Then we will talk about a little bit about chemical equilibrium. if you have a chemical reaction happening, and you have probably seen this stuff in your undergrad. If not, it's a good idea to know what it is. So we'll talk about equilibrium constants and how do they relate to free energy, and very briefly about the concept of activity. So yeah, let's fix it. Next class 11:15. I think that will do. You can just agree. So next class we start at 11:15. We'll go till the end, and that's gonna be our December 6th class. That will be the last new material that we do. December 8th, we will do a recap of the full semester, and December 14th is your exam. Okay, any questions? Bye, Omar. We already left. Hi, there.